and in this very short tutorial, I'll try to introduce you to the automated negotiation field. I will not try to be exhaustive, which is impossible in a short tutorial. The main goal here is to give you the vocabulary used in the field and point to some other resource in which you can get more information. So I'll speak about these things. First, I'll introduce the concept of negotiation, what negotiation is. I'll speak about some of the negotiation protocols most commonly used. I'll give very little discussion about the game theoretic analysis of negotiation scenarios and some of the very basic strategies for a specific scenario, a specific protocol that's used a lot in the automated negotiation, negotiating agents competition. And then I'll point you to some of the challenges in automated negotiation that are becoming more important in recent years. So what is negotiation? Negotiation is foremost a method to achieve agreement. So if an agent doesn't want to achieve agreement, it doesn't need to negotiate. But why do we need to negotiate when we want to achieve agreement? Because we are assuming that we have self-interested actors. So each actor here, that's an actor. So an actor can be like this guy, can be a person. Okay. Or it can be an institution. And the goal has some goals. He wants to achieve something. And this is represented internally by a utility function, which gives it a preference over possible alternatives. And to achieve this goal, it needs to do something that involves another actor, this actor in this case, and this other actor again can be a person or an institute. In automated negotiation, we assume that one of them or both of them employ automated agents to negotiate on their behalf. These automated agents have some protocol between them that describes how they go about this negotiation process. So if we assume that the two utility functions representing the preferences of both actors are the same, the negotiation is trivial, right? The first guy will propose something which is the best thing it can achieve, and the other guy will accept it because it's also the best thing it can achieve. Only when these two utility functions are not the same, when there is some conflict between the preferences of the two actors, is negotiation necessary. And the goal of negotiation in this case is to achieve win-win agreements. Now it is not very clear what does it mean. You may have an intuition about a win-win agreement, but we will make it much more concrete later. Okay. So let's go into some more details about how a negotiation scenario is represented. So a negotiation is represented by this tuple. The first thing we need is to know how many agents or actors are there. Notice that there is a 1-1 mapping between agents and actors. And in this very short introduction, I will not distinguish them very carefully. Sometimes I speak about actors, sometimes about agents, but they are mostly the same. And as you can see, it can be any number that's not one. So we can have bilateral negotiation between two actors or multilateral between 3 or 4 or 5 actors. And usually there is an allowed time for the negotiation. So negotiation can go for some predefined amount of time, let's say 3 seconds, 5 minutes, or maybe there is no constraint, can go forever. And there can be an allowed number of rounds for the negotiation. This is just how many rounds are there. And that's usually an integer, and the concept of a round is defined by the protocol. What is a round is something that the protocol defines. Then there is the outcome space, and that's a very important concept. The outcome space, usually represented by this capital omega, is all possible outcomes. So these are all the possible things we can agree on. And usually there is an implicit outcome, I will call it phi here, which signifies disagreement. By the end of the negotiation, we may disagree. And in this case, we say that the final agreement is phi. Then we have the negotiation mechanism. all protocol, we will use these two words interchangeably, which means the way in which the agents interact to do the negotiation. And as we will discuss later, there are many types of protocols. Then there are preferences. Notice that here preferences are defined for the actor. The agent itself is just a piece of software. It doesn't have preferences. Preferences are defined for either the human using the agent or the institute using the agent. And we call these preferences P tilde. Then there is the information available to the agent about the preferences of some actor. So the agent may know the preferences of its own actor, or it may not even know the preferences of its own actor. And in most cases, we assume that it does not know the preferences of the opponent. In most cases, we have this non-preferences assumption that the agent knows the preferences of its own actor. So it knows its own utility function simply. But that's not necessarily the case. That's an assumption. The first thing we need to understand is how to represent preferences. And there are many representations of preferences for negotiation. The simplest one is partial ordering, which is usually represented by this greater than simple. When we say that two outcomes have a partial, when we say that there's a partial ordering over some outcome space, we say that if we have any two outcomes, we can define which of them is greater than or equal to the other. Ranking is a special case, which is a total ordering over a subset of omega. It needs not be over the whole of omega. The most widely used way to represent preferences is a utility function. And the utility function simply defines a numeric value for every outcome in the outcome space. So it's a mapping from the outcome space to a set of numbers. And in many cases, this is usually normalized between 0 and 1, but not always. So that's what we call a utility function. We can have a more probabilistic version of utility functions. And in this case, this probabilistic utility function is a mapping from the outcome space and all possible utility values to a value between 0 and 1, under the usual constraints that all probabilities must sum to 1. So it just tells you that what is the probability that a specific outcome has a specific utility value. The non-utility function assumption, again, that's an assumption, but it's widely used, is that the utility of the agent over time is fixed and it's equal 1 when the utility value considered is actually the utility of the actor and 0 otherwise. What this complicated piece of math is saying is just that the agent knows the utility function of the actor. Okay? So we discussed before that any negotiation has agents. Here I'm speaking about two agents, but they can be many, and a protocol. So some examples of negotiation protocols are the alternating offers protocol, sometimes called the bargaining protocol, single text protocol, which is widely used in real-world negotiations in many cases when there is a mediator, and many others. And the other thing is a negotiation strategy. A negotiation strategy is the strategy used by the agent. So it defines how the agent behaves during a negotiation. Okay, and there are many types of strategies. The simplest ones are time-based strategies and tit-for-tat like variants, or sometimes they are called behavior strategies. There are many other types of strategies, of course. And we will not describe all of that, but we will try to give one example of each one of these, just to give you a more concrete idea. Finally, there is this graph that you will see in almost any automated negotiation paper. And you need to understand what does it mean. So in this graph, we represent on the x-axis the utility value of one agent, on the y-axis the utility value of the other. Here we assume that that's a bilateral negotiation. And every point here is an outcome. So let's say that we are negotiating about buying something. And for a specific price and quantity, represented here by, for example, this point. Okay, actually there are many points here, but let's just speak about any one of them. We can say that the utility for this agent is 0.35 and the utility for that agent is like between 0.2 and 0.3. Okay, so that gives you for each outcome can be represented here. So that's just a scatter diagram of all the outcomes. And using this figure, we can show many of the most important concepts in negotiation. The first one is this part here. This is called the Pareto front. And the Pareto front is a set of outcomes that that are not subsumed by other outcomes. By that I mean, you cannot improve the utility. If you look at any outcome here, let's say this one, you cannot improve the utility of the X agent by going to the right without also decreasing the utility of the Y agent, because you have to go down to find some outcomes. There are no outcomes in this Pareto. So that's the Pareto front. And if you get to an agreement that is not in the Pareto front, it means that you are leaving money on the table. Assume that you got to an agreement here. We negotiated and got this agreement. We could have, without decreasing the utility of the Y agent, got that agreement. Or we go without decreasing the utility of X agent, we can get that agreement. So the main goal of design, when you are designing a protocol, is to make it easy for agent to find the Pareto front. And notice that that is not an easy problem, because each agent can only see the projection on its own axis. It cannot see the utility of the other agent in most cases. Okay? So that's the Pareto front. And there are some very important points on the Pareto front. One of them is the point of maximum welfare. So what is welfare? Simply, it is the total utility received by all actors. So it's simply the sum of the two values here, X and Y. And in this case, the outcome with maximum welfare may be around like here. There's some other important point, which is the Nash point, the Nash equilibrium, and there are other kinds of equilibria like the Calais point. And these points represent more or less fair agreements. We will speak about them in a little bit more details later when we describe the Nash bargaining game. Another thing is the surplus utility. So the surplus utility is just the utility above the disagreement utility. What is disagreement utility? The utility you will get if we agreed on phi. If you remember, phi means no agreement. If we got no agreement, each agent will get some value. We call it the reserved value of the agent, or the reservation value. And the surplus utility is the difference between the utility you get and your reservation value. So in this case, let's say that before negotiation, this agent knows that it can get this amount of utility. So even it got disagreement, it can get 0.57 or something. Then any outcome here for it is really bad. It's worse than if they didn't negotiate at all. Okay? Let's say that the agreement was here. So the surplus utility is simply this distance, the difference between the reserved value and the agreement we got. Okay? Another very important concept is the subgame perfect equilibrium. And this concept is a Nash equilibrium in every subgame. We will use that when we speak about the game theoretic representation of negotiation, but it's not necessary to understand to start developing negotiation strategies, to start working in this. So let's see. There are several types of automated negotiation problems depending on all of these factors we defined for negotiation. So depending on the negotiator type, there is agent-agent negotiation. That's a clear automated negotiation case. But there is also agent-human negotiation. In this case, psychological effects become important. When one of the agents is an automated agent, but the other one is actually a human. In this case, it's important to take into account the fact that human can get offended. And similar psychological quirks of people. The number of negotiators, we have bilateral negotiations and multilateral negotiations. The name is very clear. Bilateral negotiations between two agents and multilateral negotiations between more than two agents. And the outcome space, usually we speak about single issue outcome spaces. And single issue outcome spaces, in this case, we just have a set of outcomes that do not have internal structure. Or multiple issues negotiation spaces, in which we have some internal structure. We have a set of issues, and each outcome is a complete assignment to each one of these issues. Okay? And then the protocol type. There are several protocol types here, as we said, but in general, we can classify them into either mediated protocols or unmediated protocols. In unmediated protocols, the two agents exchange some messages directly. There is no third party. There is no trusted third party. In mediated cases, we have a trusted third party. So if you want to start working in negotiation, it's useful to have some platform to use, some existing tested platform that can help you build your protocols, your agents, and connect things together. There are two important platforms that we'll speak about. The most important, of course, is Genius, which is the oldest. And there is a newest version of it called Genius Web, which is the one used in the first league of the ANAC competition last year and this year. This is a Java-based negotiation platform. And there is also NegMAS. And NegMAS is a Python-based negotiation platform. I will use NegMAS in this tutorial just because I am more comfortable using Python instead of Java. Also, it's very easy to show things on it. So let's just see the part that we spoke about now on NegMAS. How does this thing look? I will not describe how to install it. It's simply pip install NegMAS. It's that easy. But and also I'll use the overview document of the NegMAS documentation in this tutorial to describe the basic things we spoke about. So you need, if you want to use NegMAS, of course, you just need to import it. Here I'm importing something called an outcome, and then I'm importing everything just to make it easier to go over this negotiation. Then the first thing we speak about is the issue. An issue, as we said before, is just one dimension of the outcome space. And you can define several types of issues. So here, this is issue one. It has values to be or not to be. And it doesn't, here we didn't give it a name, but we can give it a name. So it's issue 2 is just the same two values, but the name is the problem. So you can see here, when you print that, it gives you a random name for the first one and the problem for the second one. And there are two values. This is a discrete issue because it just takes one of these two values. You can also tell the system that the issue has values of 10. This means that it has all the values between 0 and 9. Okay, the 10 values between 0 and 9. So that's an example of this case. You can give it a tuple. So here that's a tuple of real values. So it's all the real values between 0 and 1. Or it can be a tuple of integer values. You can say, for example, it is all the integer values between 1 and 7. So now you define an issue. Okay, and if what is an outcome space? It is simply a list of issues. A list of issues is an outcome space. And the issue class gives you some useful functions. For example, cardinality is used to find what is the cardinality of the issues. You know, the first one, to be or not to be, had a cardinality of 2. The second one, from 0 to 9, had a cardinality of 10. But the third one, because that's a continuous issue, it has an infinite cardinality. Okay. You can also check the type of the issue. You can say, is it discrete or not discrete? What is the type of the issue? Is it continuous? There are many functions that you can use. You can look at the documentation of the issue class for those, but I'm not going to go into details into these. This is an example of an outcome space. And an outcome space is nothing more than a list of issues. And what about a single issue space? It's a list of a single issue. Okay. And here you can say that you can have, again, there are some functions. These are class methods defined on issue that gives you some information about the issue space. For example, how many outcomes are in the issue space. The first issue space has issue 1, 2, 3, and 4, and one of these is infinite because 3 was continuous. That I think 4 was continuous, so that's why it's giving infinite. But the other one has 2 issues, 10 issues, and 2 issues, so the total is 40. Actually, that's 10. Let's correct it. You can pick random valid or invalid outcomes from the issue space by just saying I want a random valid issue from the value from the first issue, or a random invalid value from the first issue. Okay. You can enumerate issues, all of that. The second thing we spoke about was outcomes. What is an outcome? It's a complete assignment to the set of issues. So here, that is the first one here is a valid outcome to an issue space with two issues. So it's here a dictionary, and the keys are the names of the issues, and the values are the values of these issues. Okay. Notice that this outcome, which we call invalid outcome, is invalid because the number of items issue had a value 10, but when we define it, it had the values from 0 to 9 only. So that's an invalid outcome. Okay. And you can actually ask the system. You can give it as an outcome space, again, just a list of issues, and tell it, is this a valid outcome? And it will tell you whether an outcome is valid or not. Okay. And you don't need to define outcomes by dictionaries. You can use lists, or you can use tuples. In this case, you lose some expressibility because you cannot say the names of the issues, but the names of the issues are simply taken from the issue space itself. So here, this is the same as the issue space we defined before. It's as if we are defining a dictionary, and we are giving the names of the issues explicitly to these three values. So the rest of this part will just speak about some of the functionality available in NegMAS to help you deal with outcome spaces, define ranges on the outcome spaces, subspaces, combined spaces, things like that. The other thing we spoke about was the utility functions. So in NegMAS, there are two types of utility values that are supported. The first one is called utility distribution, which is a distribution, the probabilistic utility distribution we showed in the presentation, and a utility value, which is simply either a utility distribution or a float, a real number. Okay, so there are many types of utility functions that you can define. Here I'm just creating a new utility function. So inherit from utility function, and this utility function is called const utility function. It is always giving the same value for any outcome. And you only need to override the eval method, which tells it what is the offer. Given an offer, here an outcome, it just gives you some value. And this one is returning 3 multiplied by the cost of the offer. So actually, it is not a constant utility value, right? It checks the cost and multiply the value by 3. So if you now create this utility function and you calculate the utility function of some outcome like this one, which does not have a cost issue, it will return none because it cannot calculate it. But if it can, like in this case, there's a cost issue and it has a value of 10, it simply multiply it by 3. Okay. And you can define any form of utility function. There are some built-in utility functions. Here is a utility function with an internal state. We call it a moody utility function. Depending on its internal mood, it changes the value of different outcomes. And we spoke about different types of preferences. So there are partial orderings, there are rankings, comparisons, and all of these. You can define utility functions for these different types of preferences in NegMAS. I'm not going into details. You can go into the representation here and read it in the tutorial. But I'll speak a little bit about this type of utility functions. It's called linear aggregation utility function because it's very important. In the linear aggregation utility function, the utility of an outcome is defined as just a sum of some weights multiplied by some function applied to each issue value. So if I have 3 issues, for example, there are 3 functions that map these 3 issue values into numbers. These numbers are then multiplied by weights, and that gives you the utility function. This type of utility function is used in a lot of research, and you can find it everywhere. It's supported internally in both Genius and NegMAS. Here is some examples. So this is a buyer utility function. It represents the utility value of someone who wants to buy something during a negotiation. And let's see how is it defined. It's a linear aggregation. And it says that for the price, that's a buyer. So it wants the price to go down. That's why for the price, it takes minus the value of the price. So that means that lower is better. right? And for the number of items, it wants to buy as many items as possible. So it says that for the number of items, I just want it to go up. I want to buy a lot. But the value of this is half the value of, that's the weight factor. The value of this is half the value of the price to me. And about delivery, delivery is a discrete value issue in this case. It has two values, delivered or not delivered. I want it to be delivered. So I give it 1, and if it is not delivered, I get a 0. And then simply the sum of these three numbers give you the utility value of any outcome. So here, we are asking the system to, first I need to run that. We're asking the system to give us the buyer utility of this thing. The price is 1, the number of items 3, and the delivery is not delivered. It says it's 0.5. So what about the same thing, but just make not delivered here becomes delivered. It says it is 1.5. It's now better by 1, which is this one here. Okay. So that's how you define utility function. There are other types of utility function. That's nonlinear version. There is hyperrectangles. There are many types of utility functions. We will not go into details about them. And these are all the types supported in NegMAS, already implemented. And of course, you can add to them, and we showed you how to do that. And there are some tools that are available to help you understand your utility space. If you remember the figure we showed with the two utility functions in X and Y, you can draw this figure for any given two utility functions or for any given negotiation. There are methods to calculate the Pareto front, to create a discounted utility function, to normalize utility functions between 0 and 1, even to sample outcomes with a given utility from a utility function, given a utility function, or to calculate the range of a utility function, the minimum and maximum. Okay. So that's about the utility functions and outcome spaces, and let's go back to the rest of our tutorial. I'll speak about negotiation protocols now. And as we said, there are unmediated and mediated protocols. And the most important feature of unmediated protocols is that there is no central coordinator. There are some exchanges that happen between the two agents, and there is no one else involved. So agents negotiated by exchanging messages, and all proposals come from negotiators. There is no source of proposals other than negotiators. And there are many examples of this. The Nash bargaining game, which is, I think, the oldest type of negotiation game, is a single iteration, single issue bilateral protocol with complete information. So in this case, both agents know the utility function of the other agent. And the Rubenstein bargaining protocol and the stacked alternating offers protocol, which is the most widely used protocol in automated negotiation these days. And you can see these are the references of these protocols if you want to know more about them. The mediated protocols are protocols in which there is some mediator. The role of the mediator varies depending on the protocol. Sometimes the mediator is the source of all proposals. So the mediator proposes something for both agents, and if both agree on it, it becomes an agreement between them. And then if one of them or both rejected it, the mediator just changes the offer. So that's what's called the single text protocol. And in the real world, single text protocol is used in lots of cases when a third party actually exists and can be trusted by both parties. So game theoretic analysis of negotiation is actually very old. And one of the oldest things we studied in this is the Nash bargaining game. I want to describe this in a little bit more details because it gives us some intuition about negotiation in general. So in this game, it's a single step. So first we have a single round and full information bilateral negotiation, which means that all agents know the utility function of the other agents. Both agents know the utility function of the other agents. It has two utility functions, U1 and U2. And the outcome space is just numbers between 0 and 1. So you have numbers between 0 and 1. So you can represent the outcome space by this square here, all the values between 0 and 1 on X and on Y. Any point here is a possible outcome. So that number of outcomes is infinite. And usually there is what we call a feasible set. A feasible set of agreement is a set of agreement that are allowed by the protocol. And a very common example is that the total utility received by the negotiator is less than or equal to 1. So this is the green line here. Anything here under the green line is a feasible outcome. Anything above the green line is not a feasible outcome. Okay? Now what happens is both agents will just offer some outcome. So I will say, I will take 0.4 and you say I will take 0.7. Then if the sum is feasible, this outcome is actually becomes an agreement and becomes binding. So I will get the amount I asked for and you get the amount you asked for. But if it is not feasible, the whole thing fails and there is disagreement now and no one gets anything. Actually, what everyone gets in this case is the reservation value, which is called here the disagreement point. So at the disagreement point is defined as just the sum of the two utilities when there is no agreement. Okay, so that's the utility value received by the two players in case of disagreement, and this sum means that that is the welfare, the total welfare. Okay, you can define the disagreement point as a point in 2D space. In this case, here this agent had this utility as a reservation value, and this agent had this utility as a reservation value, so that's the disagreement point. Actually, in this case, we should say that D is not, there is no sum here. It's actually a point, a two-dimensional point. Okay. So any outcome under this, in this area, any outcome in this area under these two lines is actually non-rational, right? Because no one should offer something less than its own reserved value, and they know the reserved value. So people will offer something here. And the Pareto front in this case is this green line, right? Because if we agree on, if I propose, for example, 0.4 and you propose 0.6, we are on the Pareto front. We cannot improve one of our utilities without decreasing the other one. And no one is lost. Nothing is lost. There is no money on the table. That is a win-win deal. Because the agreement we have is better for both of us than not having an agreement. So any point in this triangle is actually a win-win deal. So we said that the goal of negotiation is to find win-win deals, but not any win-win deals. We want to find the best win-win deals. These are the ones on the Pareto front. Okay. So that's a Nash bargaining game. And actually Nash solved this game and found that if we play this game, there is a single Nash equilibrium. People familiar with game theory will understand what I mean, which is a set of policies for both agents that you cannot improve without decreasing the utility of at least one of the two agents. And it's simply that. You notice that this is a definition of the surplus. So you should simply multiply the two surpluses and find the outcome for the omega 1 and omega 2 given to the first one and the first guy and the second guy that will maximize this. Maximize the product of all the surpluses. And in the figure we showed before, this figure that I told you is always everywhere, this is the Nash point. As now we know these two utility functions, we know the surpluses because we know the reserved values, we can calculate the Nash point. And it is usually associated in the minds of people with fairness. Nash points are usually associated with fairness, and you can see that intuitively because it simply maximizes the product of what each one of us could have gotten from this negotiation, assuming the reservation values we had. So this would be maximized when we both got good surpluses. If one of us got bad surplus and the other one got high surplus, this value will not be maximized. There are other solutions under different assumptions. For example, the Kalai-Smolodinsky point. Sometimes it's just called the Kalai point, and this is how it is defined. There's no need to go into these the details of these points, but you can read about them more in the tutorial in NegMAS documentation. A more advanced protocol, the Rubenstein bargaining protocol. In this case, the two agents are also sharing a pie. It's the same thing. and we don't want anything to be lost. And each agent is under different time pressure. That's a difference because there's a different time pressure for each agent. And there are two types of time pressures, exponential and linear. Again, I don't need to go into these details. I don't want you even to understand these details. It's not important for our goals in this tutorial. Just to know the flavor of the Rubenstein bargaining protocol. Just there is time pressure on both agents, and it can be different. And the actor's initial utility is assigned part of the pie. So that is simply the utility of the actor when we start a negotiation. Each one have some assigned part of the pie, and then we change the assigned part during the negotiation. And can you offer you to get this a specific assignment, and then you offer me back a different assignment until we get to agreement. Okay, the time pressure and utility information are common knowledge. That's a specific assumption about the Rubenstein bargaining protocol. Both agents know the utility functions of the other agents, and both agents know that the other agents know their utility functions. So that's the definition of common knowledge. And there is no externally imposed time limit, so you can negotiate forever. And what did Rubenstein prove? That in this negotiation, there is an optimal solution, which is that is the optimal solution. It's actually a one-step negotiation. Even though we have an infinite time, we can negotiate forever. It doesn't make sense to negotiate forever. The optimal solution is that the first guy should offer this and the other guy should accept it. And that's it. That's in case of exponential discounting, and that's in case of linear discounting. Again, it's not very important to understand these equations or what they represent. The only thing that's important here is to notice that in this case, even when there is full information, there's no need to have rounds of negotiation. Just one negotiation is enough. So if that is the case, why do people negotiate? Because we don't have complete information. We don't have complete information. That means that we don't know either the utility function of the other agent or sometimes even the utility function of ourselves. And that is a reason that makes it necessary for us to negotiate over time. Now I'll speak about the most commonly used protocol, and actually that's the protocol used in the ANAC competition, I think in all the leagues of ANAC competition. And as you can see, that's a full implementation of the protocol, except for some very few quirks. So it's a very simple protocol. What the protocol says is that the two agents keep exchanging offers until one of them accepts the offer proposed by the other guy, that's if it's bilateral, or until everyone accepts one of the proposals, if it is multilateral, or the negotiation times out. So here, if timeouts, and timeout is just the number of rounds or the wall time constraint we spoke about before, if the negotiation timed out, say it's timed out and return. Otherwise, this means take the next agent, right? If you have set of n agents, take the next agent. And ask this agent to respond to the last offer we have. So what should be the first offer? Just the first offer from the first agent. That's the initialization. And ask the current agent to respond to the offer that we have now. It can have one of these responses. It can say accept. In this case, the number of agents increases by 1. And if the number of agents that accept equals to the number of agents, which means that I offered something and everyone else in the negotiation accepted it, then return this offer as an agreement. Otherwise, if the response was end negotiation, then return failure, means that one of the people left the room. Now, one of the people don't want to continue negotiation. Now the negotiation completely fails. And the other possibility is that the current agent rejected the offer. In this case, ask them to give a counter offer. And now this counter offer becomes the current offer for the next negotiator. Okay. So that's the alternating offers protocol. And there are some common decompositions of the opponent of the agent structure in this case. You don't need to use this decomposition, but it's useful to understand it because it gives you some intuition about some of the existing negotiation strategies. This very common decomposition called the Boa architecture divides the agent into the following components. back. Yeah, here. The first one is the opponent model, which tries to understand either the behavior of the opponent, their strategy, or their utility function based on their behavior. The second thing is the bidding strategy. That's the thing responsible of giving proposals. So when proposal is called, this is what's implemented in it is what we call the bidding strategy. And finally, there is the acceptance strategy. And the acceptance strategy is the strategy that tells you when to accept offers. And all of these need to know the domain, which is the outcome space, and the utility space, which is the preferences represented by utility function, and the bidding history, which is what happened before, either in this negotiation only if there is no learning between negotiations or in all past negotiations. So we can now go to our tutorial here and continue it. The first part here speaks about the possible responses that the agent can give when it is asked to respond to an offer. And we said these are accept offer, reject offer, end negotiation. There are some extra responses here we didn't speak about for timing control, but they are not necessary to understand at the beginning. Okay? So in NegMAS, the agent that actually engages in negotiation is called Negotiator. The word agent is reserved for a more complex entity that we will not go into in this tutorial. So the Negotiator is the agent that actually engages in negotiation. And the negotiation protocol is called a mechanism. Okay, we said that mechanism and protocol are interchangeable. There is a specific type of negotiator in NegMAS called genius negotiator, which allows you to connect to genius agents. So you can use genius agents as negotiators in NegMAS. So let's just see a simple negotiation. Here is, we spoke about the stacked alternating offers protocol. In NegMAS, it's called SAO mechanism, for stacked alternating offers mechanism. And here I'm creating a mechanism, and I have to define the outcome space. So I said that the number of outcomes is 6. This means it's a single issue space with outcomes 0, 1, 2, 3, 4, 5. Okay? And n steps is the number of rounds allowed. A round is called a step in NegMAS. It's called the round in Genius. And you can also give a time limit, like how many minutes will this negotiation run for. Then you add negotiators to the mechanism. Here we create a specific type of negotiator called a limited outcomes negotiator. This limited outcomes negotiator is constructed by a set of outcomes. Here it's 2, 3, 5 for this agent. It will always offer one of these, and it will only accept one of these. And whenever it's offered any of them, it will accept it. So it's a very, very simple type of negotiator. It has a set of outcomes that it's willing to accept, and it will reject everything else. It doesn't even need a utility function. It doesn't differentiate between them. Okay? That's equivalent to saying that its utility function assigns a value of 1 to these outcomes and of 0 to everything else, and it assumes a reserved value of, say, 0.5. So it will never accept anything else, but will accept any of these with the same probability. So we add 2 of them, and notice that they have a common outcome here, 3, right? So 3 is here and here. Both of them may offer it, both of them may accept it. Then we call run, which runs the mechanism, and we check the state. And from the state, we just check the agreement. Let's run that. Yeah, they agreed on 3 as expected. Okay. This tutorial will then go on to describe how you define new mechanisms, and you simply need to override a single function called round. And this is another implementation of alternating offers, but now it is parallel alternating offers protocol, not stacked. So it doesn't move serially, but when some offer is given, it is all agents are asked in parallel to either accept or reject it. And that's how it is implemented. It's short, but I'm not going into details of that because it's not important to understand the basic idea of a negotiation protocol. And here we just create this protocol, and to use it, it's exactly the same thing. Create an object of the mechanism, attach negotiators to it, run it, and look at the agreement. Okay. So actually that is the most important part of the tutorial. Here I'm speaking about some specific bidding strategies that you can think of, about. and that people have used. So one of them is the time-based set of strategies, and there are many time-based strategies. The main factor here is that the behavior of the agent doesn't depend on the partner. Sometimes it's called opponent, sometimes it's called partner, the other guy in the negotiation or the other guys. We don't care about the offer. We don't even look at them. We define some utility value that we are willing to accept at any point, and we then usually concede by reducing this level that we are willing to accept over time. So here it shows that the relative time of the negotiation, which goes from 0 in the beginning to 1 at the end. And these are 3 time-based strategies: Boole, linear, and conceder. So the conceder agent here just goes down really fast. So they are willing to accept something of a utility of 0.6 almost immediately. And then it goes down slowly to the reserved value. Of course, it doesn't make sense to concede less than your reserved value. The Boole, on the other hand, doesn't concede in the beginning, but then concedes fast near the end, and linear concedes linearly. Of course, there are many possibilities in the middle. So these are time-based strategies. Behavioral strategies there are many types of behavioral strategies which depend on the opponent behavior. And one of the simplest ones to understand is the nice tit-for-tat strategy. That is a reference for it. Again, I keep doing this. And what it does is it simply concedes as much as the opponent, and it does not retaliate. So you can read it in details in this paper, but I just wanted to point out that it's not very hard to define strategies that depend on the opponent behavior. For opponent modeling, there are many ways to think about opponent modeling. So you can model the opponent preferences, their utility function, their strategy, the probability they will accept your offers, their future offers. You can even define a set of opponent types and try to convert it into a classification problem. Which type of opponent am I facing? All of these things have been tried. And when do you do the opponent modeling? Sometimes you do it before negotiation, and sometimes you do it during the negotiation. Of course, during the negotiation is the most widely used strategy. And the data you use, either this negotiation or all past negotiations, this opponent or a set of opponents that are similar, or everyone else. And when you are using past negotiations, you may just use agreements at the end or all exchanged offers to learn the opponent model. So these are some examples of opponent models. I'm not going to speak about them. And then the third component of the agent is the acceptance model. And these are some of the simplest ones. So here it says, accept if the utility of the offer is greater than my previous offer. That's one concrete acceptance strategy. If you offer me something that's better for me than what I just offered you, then I accept. I was willing to accept what I offered, so I should accept something better than my current offer. So what I'm about to offer, in this case, I have to call the offering strategy first, find what I'm about to offer, and if what you are offering me is better, I will accept it. The expectation, so the best offer I expect to receive, but to do that, I need an opponent model or some threshold. That's what's used usually with aspiration or with time-based agents. So there's some threshold. This can be a constant. So if maybe a fraction of the maximum utility. If you offer me something above 0.7, the maximum utility I can get, I will accept it. That's an acceptance strategy. It can be monotonically decreasing, like the time-based offering strategy we spoke about, and predictive. So it predicts the expectation and use that to define an acceptance strategy. Okay. Some of the current challenges in automated negotiations are negotiation under uncertainty, preference solicitation, and concurrent negotiation. So in negotiation under uncertainty, the challenge is how to negotiate when you have just partial information about your actor's utility function. Until now, we were assuming that we know our own utility function, but what if my knowledge about my utility function is not perfect? So this was actually the game that ran in the ANAC competition 2019 main league. The results were announced in Ishikai at that year. We got some strategies for this type of problem, but it's far from being solved. It's far from saying that we know how to negotiate under uncertainty. Actually, we don't even have a solution for negotiation without uncertainty. So some of the things is to regress the utility function for outcomes using polynomial models. These are things that were actually tried using Gaussian process to create a probabilistic utility function and then use that for negotiation. Preference elicitation is a related problem. Here you have also uncertainty in user preferences, but you are allowed to ask questions to reduce this uncertainty. Again, that was the game of the ANA competition main league in 2020, just last year, and it's again far from being solved. There are many types of questions you can ask. For example, you can ask about utility values, about utility constraints. Is the utility of some outcome better than a value or not? Or even it's just utility comparison compared to outcome for me. Usually the questions are assumed to have a cost, and your goal is to maximize utility while minimizing cost. And finally, there is the concurrent negotiation problem, which happens a lot in business. In the concurrent negotiation problem, you have one agent negotiating with multiple agents at the same time. And the supply chain management league of the ANA competition is an example in which you see concurrent negotiation problems. So the point here is that you want not to get the best agreement on one negotiation, but to get the best set of agreement on multiple negotiations. And in this case, your utility function may not even be defined for each one of these negotiations independently, but only defined for the complete set of negotiations. So these are some of the references. I will actually put a link to these slides and to the tutorial and the notebook I used in it, so you can reference them later. Okay, and thank you.